All right. Well, I'd like to welcome all of you to the Simons Center for Geometry and Physics and to this Della Pietra lecture. The Della Pietra families support this lecture series in part to help bring the excitement of science to students, high school students and college undergraduates. So I'm especially pleased to see so many students here today. Before I introduce the talk that you're about to hear, let me tell you about something that's going to happen immediately after this talk. So right when Professor Kirshner finishes and has answered all your questions, there will be a short presentation by Professor Tony Phillips from the mathematics department here at Stony Brook about work of a sculptor. I don't know if you saw coming in, but right out here, about 100 yards, is a huge, huge sculpture in the form of a torus. It was made by Hilleman Ferguson. It's just being installed. Other of his works, much smaller, this one weighs 20 tons and is about 25 feet tall. So the smaller works by Ferguson, some of them are in our gallery, and they're all mathematically inspired, and Tony Phillips will talk to you a little bit about the mathematics behind these sculptures. So that's immediately after this talk. That'll be a shorter talk. Yeah, about 10 minutes. And then you'll be free to go to the gallery and look at the pieces. Well, back to today's Della Pietra lecture. You're in for a treat. When we started this lecture series, I immediately thought of Professor Kirshner as a lecturer. I had heard him talk in Nijmegen, Holland, a little over a year ago, and I immediately knew he'd be an ideal speaker for this series. So let me tell you a little bit about his background. He is the Clowes Professor of Science at Harvard University. He's a 1970 graduate of Harvard College. He received his PhD from Caltech and recently received an honorary Doctor of Science degree from the University of Chicago. He served as president of the American Astronomical Society from 2003 to 2005. He's a member of the National Academy of Sciences and of the American Philosophical Society. He shared the 2007 Gruber Prize for Cosmology and received the 2011 Heineman Prize for Astrophysics from the American Institute of Physics. Two of the recipients of the 2011 Nobel Prize in Physics, Brian Schmidt and Adam Riess, were his graduate students at Harvard. He's a frequent public lecturer on astronomy. He teaches a large undergraduate general education course at Harvard called The Energetic Universe, and he's the author of a popular level book, The Extravagant Universe, Exploding Stars, Dark Energy, and the Accelerating Cosmos, and I'm sure you will all go out and buy that book immediately after this lecture. It's still in print. Okay, these lists of accomplishments and honors indicate the important influence Bob Kirshner and his work have had on the field of astronomy. They also indicate his ability to explain his field to general audiences, and I'm looking forward to an exciting and inspiring presentation, and I believe at the end of it you will agree with me that he's an ideal lecturer in this series. Please welcome Professor Kirshner.
Thank you. Well, thank you for that warm introduction. After that, I can hardly wait to hear what I have to say. And I would recommend to all of you, if you're offered an honorary degree, which involves no tuition and no exams, go. That's a very good thing to get. What I'm going to talk about today is the history of the universe. That's a 13.7 billion year history, and I'm going to try to describe it in 40 minutes. To do that, I will leave out some of the details, like the names of my collaborators and so on, and I will get right to the important business. Now, what you see here is a galaxy, something like the Milky Way galaxy, a system of 100 billion stars or so. And what you're seeing in this picture is something quite interesting. One of the stars in that galaxy, this one, is shining as brightly as about 4 billion stars like the sun. This is the eruption of a supernova in that galaxy. And as I'll show you, it's the observation of these exploding stars that we've used to measure distances in the universe, to figure out the history of cosmic expansion, and to find the surprising thing that the universe is not slowing down due to gravity, but the expansion of the universe is actually speeding up due to something else that, out of ignorance, we call the dark energy, but we don't really know what it is. So that's my plan for the next 40 minutes, and then if there are any gaps in the explanation and you have any questions, I'll try to answer those. Then we'll find out about the art piece. Okay, so if you think back about 100 years, well, most of us can't remember 100 years, but it turns out this is the situation 100 years ago. Astronomers told the physicists that the Milky Way, the galaxy in which we, the sun, and the Earth are located, was the universe. And so this is a modern picture that shows the Milky Way. You see it in the summertime sky here in the northern hemisphere if you're at a dark place. And what astronomers told the physicists was that that was the universe. We were surrounded by some kind of a void, and that the job was to explain this phenomenon. However, that turns out not to be the whole story. Although in 1917, that's what astronomers told Einstein, one of the interesting things that I'm going to mention is that technology has advanced quite a bit since 1917. And as a result, we can now see what Einstein was thinking. And what Einstein was thinking back then, based on what the astronomers told him, was that the universe was the Milky Way, and the Milky Way is not expanding or contracting. So he thought, well, the universe must be static, standing still. And he built up a theory to explain that. But at the same time he was doing that, there were observations being done which showed that this was fundamentally the wrong picture. And one of the people who played an important role in that is this demure woman. This is Henrietta Leavitt, who worked at the Harvard Observatory and who studied a particular kind of vibrating star, the so-called Cepheid variable stars, and she found this interesting point. She said, it is worthy of notice that the brighter variables have the longer periods. That is, the stars that are intrinsically bright took longer to get bright and dim, to vibrate, to get bright and dim and bright again. And this is a key idea in astronomy. We try to judge the distances to things from their apparent brightness. So, for example, if you look out over a desert highway or off the shore and see distant ships, you can try to estimate their distance from how bright the lights appear, how bright the headlights of a car would appear, or the lights of a ship would appear. If you really know which ones are the same, then by measuring the brightness that they have, the apparent brightness that they have, you can tell which is nearby and which is far away. And this idea that there was a particular kind of star whereby measuring something that didn't depend on the distance, how long it took to vibrate, you could tell whether you were looking at an extra bright thing, a 200-watt star or a 50-watt star. You could tell what you were looking at, allowed people to use these stars to measure, to survey the properties of the Milky Way galaxy. And what they found is illustrated here, that Stony Brook and the Earth and the Sun are not at the center of the Milky Way galaxy. We do not live at the center of the universe. Well, anyway, we don't live at the center of the Milky Way galaxy. You've probably heard that the Earth is not at the center of the solar system. That's generally known. It turns out the Sun is not at the center of the Milky Way galaxy. And in a minute, I'm going to argue that it probably would be a bad assumption to think that our view of the universe, our Milky Way's view of the universe, was unique and special. Okay, so anyway, we're not at the center of our Milky Way galaxy, and these Cepheid variable stars were used to judge the size of the Milky Way. Now, astronomers usually use sort of funny units to talk about distance. You all know that light travels at the speed of light. The speed of light is a foot. That's a unit of distance used in the United States and in Myanmar, I believe. A foot in a nanosecond, in a billionth of a second. So that means when I look out in this room, I do not see you the way you are. I see you the way you were when the light bounced off you that's on its way. So the people in the front row I see as they were 10 nanoseconds ago. The people in the back row, curiously, look younger because I see the light that came from them long ago. Well, all right, only 100 nanoseconds ago. Just a joke in a room this size. But in the universe, not a joke. The light that we're receiving from nearby objects left recently. The light from the sun left about 9 minutes ago. The light from the stars that you can go out and see tonight that are in the Milky Way might be 10 or 100 light years away. And even with your naked eye, you can see galaxies whose light has been traveling to us for 2 million years. But you may remember, right at the beginning, I said we're talking about a 13 billion year old galaxy, 1,000 times bigger than the distances to the nearby galaxies. And as I'll show you, measuring those distances is a tough thing. Anyway, the tool that people had were these vibrating stars that Henrietta Leavitt had classified and shown that the bright ones had the long periods. And this was the big telescope, the greatest telescope in the world at that time. This is the 100-inch telescope. Now it's 2.5 meters. That's the diameter of the mirror down here. This is at Mount Wilson, which is up above the little village of Los Angeles in California, which at that time had a population of 25,000 and not too many lights. The situation has changed somewhat in Los Angeles. So this telescope is now more of a museum than a working facility. Nevertheless, the astronomer would go up here on this platform, I'll show you in a second, and use a photographic plate, which was a piece of glass with some horse hooves ground up to make gelatin and silver stuff in it to be developed chemically to show you where light was. The astronomer would go up here to take photographic plates. There. And here is the person who, up on that platform, here's Edwin Hubble, up on that platform in the 1917, let's say. And this is the place where the photographic plate would be put, and the eyepiece was used to keep the telescope pointed at exactly the same place as it moved across the sky, tracking the rotation of the Earth. And what Hubble was able to do, he's really wearing a nice outfit, don't you think? Riding boots and a tweed jacket. Very nice. Anyway, he was able to find some of those same stars that Henrietta Leavitt had found, but not in our own Milky Way. In these things that people called nebulae, the things that were not very well understood at the time. And he showed that they have distances which are much bigger than the distances in the Milky Way. The diameter of the Milky Way galaxy is about 100,000 light years. And as I'll show you in a second, the distance, I guess I can just do this. Here's a photographic plate. Actually, this must be a print from a photographic plate that was taken by Hubble back in 1923. And you can see he's marked these things. These are the novae. These are new stars that were cropping up that he was going to use to measure the distances. But he found this other thing that he thought was a nova, and then he crossed it out. He's writing on the glass side, on the back of the plate, and wrote var for variable. This is the first of the Cepheid variables, the same kind of stars that Henrietta Leavitt had noticed, only the first one seen in this object. And from its brightness, which was hundreds of times fainter than the objects in the Milky Way, he was able to figure out the relative distance between us and the Andromeda Nebula, M31, this thing here. So, I don't have to go back there. So here's another picture of M30. If you have a recent operating system Mac, when it opens up, it shows you M31. They've edited out this galaxy for artistic reasons. I don't know why. But anyway, it shows you this right at the opening page. Hubble used the distances of the stars in the galaxies to measure the brightness of the stars in the galaxies to measure their distances. And he showed that these fuzzy things, these spiral patches, were not part of the Milky Way.
Excuse me, I know you're not supposed to ask questions now, but why isn't the distance plus the intensity determining the brightness? So
right. If you knew the brightness, if they have the same period, they have the same brightness. You measure the period by taking photographs night after night. That's what Hubble did. So you know you're talking about the star that has the same intrinsic brightness because it has the same period from Henrietta Leavitt's law. Right. So you've got to know that other thing. And then the brightness goes down like the square of the distance. Right. Okay. So what Hubble was able to show is that we live in a universe that is not one big galaxy, but is a universe of galaxies. All these fuzzy things, this one and 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 this one, everything you see in this picture, in fact, is a galaxy, except for a very few stars in the Milky Way that are along the line of sight. Each of these is a system as big as the Milky Way, only much farther away. And it's that breaking open of the universe that took place in the 1920s to find out that we live in a universe that's made of galaxies. If you use the Hubble Space Telescope, which is named after Edwin Hubble, it's about the same size as the telescope at Mount Wilson, but it's in a much better site. It's up above the Earth's atmosphere in orbit. And you stare at a single patch of the sky for as long as you can stand it. You find that it looks something like this. There's a picture in today's New York Times that shows the result of doing this for 2 million seconds, so most of a month. And what you see in this picture is that it's a universe of galaxies. The universe is full of galaxies along the line of sight, some nearby, some far away, but everywhere you look, there are galaxies. So every little smudge, not just the big ones that look like galaxies, but every little smudge, with just a couple of exceptions, here's a star, but everything else is a system of 100 billion stars, and there are about 100 billion of those galaxies. If you take a picture of a little chunk, you measure the area, and you multiply by the area on the sky, you get an estimate for how many galaxies are. It's about 10 to the 11th, 100 billion. Okay, so that's a big change from a universe that is just the Milky Way to a universe that is full of galaxies. The other piece of it is that the universe is not standing still. Remember, Einstein thought that the universe was static. It's not, and here's the evidence. This fellow with a kind of funny name, Vesto Slipher, worked at the Lowell Observatory, which was in Flagstaff, Arizona. And he used, and he used this device, which is a spectrograph, a device that takes light from a galaxy or a star and breaks it into a spectrum, a rainbow, and then records it photographically up here at the business end. And he took the spectra of these nebulae and he found something very interesting. The nebulae are not standing still. They are moving. They are moving faster than any of the stars in the Milky Way. And almost all of them are moving away from us in a way I'll describe in a second. Their light is shifted to longer wavelengths toward the red. So here's the idea. A scientist's job is to take something beautiful, like this rainbow, and turn it into a graph. And so here you can see up here is the graph that corresponds to how much light there is at each wavelength in this rainbow. And what you'll see is that it's the usual thing. All the colors are there, except at certain wavelengths, certain colors, which are missing. These we call absorption lines because the light has been absorbed, and lines because when you make a spectrum like this, it comes across as a line. Or you see them in this graph up here as sharp dips, where there's less light coming out at those particular wavelengths or colors. Now, the interesting thing is that every atom in the universe has a particular pattern of spectrum lines that's set by the physics of the atom. So here's sodium in this star or galaxy. It's the same as sodium atoms in the laboratory, where you can measure the wavelength that sodium atoms emit or absorb light. And what Slipher found was he saw the same lines of the same atoms that we see in the sun, but they were shifted, stretched out to longer wavelengths by what we think of as the motion of the galaxies, what we call the redshift. So this was evidence, first of all, that these things, these fuzzy things, these nebulae, are made of stars like the sun, and that they have atoms in them that are just like the atoms in the sun, just like the atoms in the Earth. The laws of physics seem to be the same throughout the universe. We have the same rules, the same subatomic rules that govern the energy levels in the atoms on the Earth as in the distant galaxies. Good thing, too, otherwise this next part would get really hard. Okay, so I talked about the speed of light. You know about the speed of sound, which is sort of a metaphor for really fast also. But the speed of light is 1,000 times faster than the speed of sound. And you hear the effect of objects' motion as they come toward you or away from you on the frequency or the wavelength of the sound that's emitted. So if you stand by the side of the road and a car comes by, you know what it sounds like. It goes. If you're in the car, it's emitting, it's the engine and the tires and all that stuff's making a sound at a particular frequency, let's say. But when you're standing there and it's approaching you, you hear that shifted to higher frequency, and when it goes past you, everybody knows this, there's a Doppler shift to low frequencies. You stand by the side of the road, cars go, or if they're racing cars, they go, they hire a bigger change in frequency. So if you stood by the side of the road and you imagine what it would look like if the speed of light was 1,000 times lower, it would look like this. Cars going away from you would have red lights on the back, and cars coming, hey, it looks like that, but that's not the reason. Okay, the reason is, of course, we have colored filters on those lights. But anyway, the idea is this, that you can tell whether things are coming or going by sound. You need a radar gun, which, by the way, the local police have, to measure the speed of things with light or with electromagnetic radiation. Anyway, so you can tell whether things are coming toward you or from away from you, and Slipher did that for the galaxies. Okay, so Hubble measured the distances to the galaxies. Slipher measured the velocities. Now, if you have two lists of numbers, if you're a scientist and you have two lists of numbers, one list distances, the other list velocities, you know what the scientists will do with those lists. They will make a graph. And here it is. Here it is. This is a plot from 1929. This is Hubble's diagram, as we call it. We call these Hubble diagrams. That's why it's a little confusing. Anyway, this is the velocity up here. This is the distance out here. Now, Hubble only got a B+ on this lab report because the units are wrong. This says kilometers. It should say kilometers per second. But anyway, never mind that. Here's what he noticed was that if you look at the nearby galaxies, here's 0. So below 0 on this plot means it's coming toward you. Above 0 means it's going away from you. Okay? And you can see that there are a few nearby galaxies. In fact, M31, the Andromeda galaxy, the one that Hubble measured the distance to first, is coming toward us. Check your homeowner's insurance. And as you go farther out, even though this is a terrible plot with very few points and a lot of noise, you can see that as you look at more and more distant galaxies, the velocities are big. This is 1,000, this is 500, sorry, this is 1,000 kilometers per second. These are big compared to the velocities of stars in the Milky Way. This is in 1929, so Hubble had the idea that we live in a universe in which there's a relation between the velocity, the redshift, and the distance. Things that are nearby are moving away from us slowly, distant things moving away rapidly. Something like this, okay? So through the miracles of animation, and really cheap animation at that, I've made this by taking an image of a piece of the sky and enlarging it. And so what you see here is that there's a galaxy, and here's a nearby galaxy. As I stretch the picture out in all directions, just by magnifying the whole picture, by enlarging the whole picture, the nearby one seems to be moving away slowly because it's traveled this far in the time of the animation. Whereas an object that's farther away, say this one, which started out quite a bit farther away, moves a bigger distance. In other words, if the space is just stretching out in all directions, it looks as if the nearby galaxies are moving away from you slowly, the distant ones moving away more rapidly. Suppose I had the power to make this room twice as big. Okay? What would you see? You'd see the person who's sitting next to you, who's now 1 seat away, would end up 2 seats away. The person who's 10 seats away would end up 20 seats away in the same time. You would see everybody moving away from you, and the nearby ones moving away slowly, the distant ones moving away more rapidly. Now, at the institution where I teach, Harvard University, most of the students and all of the faculty believe that that means they, personally, are at the center of the universe. This is what I call the egotistic universe, where you think, because everything is moving away from you that you're special. Well, you are special, but not for that reason. So here's the idea. What that picture was, that animation was supposed to kind of convince you, or at least make you think, is that it doesn't matter which galaxy you pick. Every observer in a universe that's just expanding will see everything moving away from you. So you might say, well, that does mean I'm special. I'm at the center of the universe. But I told you a minute ago, you know that the Earth is not at the center of the solar system. I told you the solar system's not at the center of the galaxy. And it would be a kind of willful disbelief to think that, well, that may be true, but somehow we are at the center of the universe, where you can get exactly the same effect just by having a universe that's stretching out in all directions, expanding, in which your view is the same as everyone else's. Okay. So you remember I started out with Einstein. You can't go wrong, by the way. I have Einstein right here. And in fact, I have most of the answers to the quiz that you're going to have about this lecture are on this tie. Oh, sorry, there will be no quiz. Sorry. So anyway, here's Einstein after Hubble had discovered that we live in a universe that we interpret as expanding. So here's Edwin Hubble. Here's Humason, the guy who actually measured the redshifts at Mount Wilson. It's very cold work. Hubble didn't like that. This is George Ellery Hale, the guy who built the telescope. He's patting Hubble on the head. Good work. Here's a guy who won the Nobel Prize previously, Michelson, for measuring the speed of light that I was talking about. Here's Einstein, of course. And here's the director of the observatory. Okay, so Einstein came to Mount Wilson, where they had showed that this idea of a static universe, which he had worked out in 1916 and 17, must be wrong. Oh. Einstein felt quite bad about this. In fact, he had put a special term into his gravity equations, the equations of general relativity, to make a static universe, the so-called cosmological term. And everybody says, oh, this was Einstein's greatest blunder. So I thought I would try to find out who said that. And it turns out it's not Einstein, as far as I can tell. It's George Gamow. George Gamow wrote he did work in nuclear physics and quantum mechanics, and then he wrote a lot of popular books, including ones that I read when I was in high school that kind of got me going in this field. Anyway, in his autobiography, he says, Einstein's original gravity equation was correct. That is, before he put this extra term in. And changing it was a mistake. Much later, he says, when I was discussing cosmological problems with Einstein. I wanted to have that sentence in my book, but I couldn't do it. Okay, much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term, this thing that made the universe static, was the biggest blunder he ever made in his life. But this blunder, rejected by Einstein, is still sometimes used by cosmologists even today. And the cosmological constant denoted by the Greek letter lambda rears its ugly head again and again and again. Very good, George. Okay, so keep your eye on this Greek letter lambda, the thing that stands for the cosmological constant, the thing that Einstein put in to make a static universe. Because what I'm going to show you now is that sometimes used by cosmologists even today, this is the thing, or something like it, that we think is real based on the evidence now from the 1990s. Okay. So here's Einstein. This is at the National Academy of Sciences. And if you go there, which I recommend, and you look at his statue, it has here some equations which you may be familiar with. E equals mc squared, the only equation in Bartlett's Book of Familiar Quotations. Something about the photoelectric effect. You know, they were kind of nervous about this relativity stuff. Why don't we give them the Nobel Prize for that? Yes, good idea. Up here is the basic equation of general relativity, no lambda term in it. All right. What now? Push. Okay, so now I'm going to show you that we need this lambda, or something like it, because the universe is not behaving the way people understood in the 1930s. It's doing something more interesting. But to do it, we need something that lets us measure bigger distances. I talked about Henrietta Leavitt measuring these stars, which turn out to be maybe 10,000 times as bright as the sun, the ones that are the vibrating stars. There's another kind of changing star, a star that changes exactly once when it explodes in its death throes, so-called supernova. And there's a kind of supernova that is a real nuclear bomb where the star, which is made of carbon and oxygen, burns up to iron, the most stable nucleus, and it releases a gigantic amount of energy in a very brief time. And for a while, a single star like the sun shines as brightly as about 4 billion stars, 1 million times brighter than Henrietta Leavitt's Cepheid variables. Now, in answer to your question, I said that the brightness goes down like the square of the distance. So if it's 1 million times brighter, that means you can see it 1,000 times farther away, because 1,000 squared is 1 million. I said that the distances to the nearby galaxies were a few million light years. 1,000 times 1 million is 1 billion. So this means these are pretty good tools for finding distances that are billions of light years. And we can measure the velocities and the distances for things that are over a span of billions of years. Now you say, well, gee, that's great. Why didn't people do this in the 1930s? Part of the reason is they are quite rare. There's only about 1 per century in a galaxy. After all, you haven't seen one in our Milky Way galaxy. I haven't seen one in our Milky Way galaxy. The last one seen in the Milky Way galaxy was in 1604. It's very hard to get graduate students to embark on a project that might take a few centuries, and they just won't do it. I don't know why. The rewards would be great. Here is the guy who paid attention to these supernovae and said to Hubble, you know, you ought to be using those. This is Fritz Zwicky, who was a somewhat irascible fellow, pioneer of supernovae. He also was a pioneer of dark matter, which will play a role in our story. Turns out the Milky Way has stars in it, but it also has mass that's invisible. We know it's there because we can measure its gravitational tug. But we don't see it as stars. And he's also a pioneer of gestures. Here he is showing, this is what he called the spherical bastard. He said it's a bastard any way you look at it. And that's how he described his colleagues at Caltech, making him extremely popular. He had the idea, though, to study the supernovae. He had the idea that it would be an exploding white dwarf of the kind I described. Just to say, you should be interested in these supernovae. There was one in our galaxy that was seen by Tycho, the famous Danish astronomer, in 1572. And this is a picture taken with an iPhone at that time that shows everybody rushing out of Tycho's castle. I don't think he had a castle like that. And seeing this new star appear in the sky. And this is supposed to be Cassiopeia, the constellation. So they have happened in our own galaxy. I said that they burn carbon and oxygen up to make iron. You have iron in your blood, and it probably came from supernovae that exploded before the Earth formed. So here's a picture. If you go now to the place that Tycho was pointing to in that etching, 400 years later, there is a more or less spherical expanding shell. The green stuff in the middle is X-ray emission from hot iron, which is what we think is the product of this nuclear burning. So these things are real. And if you want to see the product of supernova explosions, you could take a look at this car. You may think it was manufactured in Detroit. But what I'm telling you is this car, which is from 1951, was manufactured in a supernova that took place before the sun formed. And so are many of the other elements, including the calcium that's in your bones, the mercury that's in the fillings of your teeth, and the iron that's in that car. Okay, enough of that. Okay, what about this history of cosmic expansion? We have to find distant supernovae, measure the distances and the velocities. Let's get on to that subject. So here's a picture taken with a digital camera, CCD camera, like the one that you might have or in your phone. And that is at Cerro Tololo Observatory in Chile. And you can see here the Milky Way over here. You can see over here the Magellanic Clouds. These are the places where Henrietta Leavitt calibrated those vibrating stars. And this is the telescope, the 4-meter telescope that we used to search for distant supernovae in the 1990s that led to this story. I said that in addition to the matter that we see, there is matter that we don't see, the so-called dark matter. And this is just an illustration of that. Here's a galaxy. Actually a cluster of galaxies, many galaxies. And what you can see is that there's this funny looking thing, these arcs, which are the lensed image of something behind this cluster, where the gravity of the objects that you do see, plus the mass that you don't see, has bent this like a lens, like looking through the bottom of a glass at some distant light source. So there's dark matter, that's real. Hubble, one of those guys, Zwicky, knew about that, and I'll show you that we expected the presence of dark matter to make the universe slow down. You know, if you throw a ball up, it comes back down. And the reason is there's gravity. The picture here is that there's matter associated with all of the galaxies in the universe, and even though the universe is expanding, that it ought to slow down due to the mass in the universe. What I'll show you is there's quite a surprise to that. So here's the idea. Here's a diagram of the universe, scale of the universe. Time, you like this? This is 14 billion years out here. This is the size of the universe. Okay. And you look from here at the present, you look back up the river of time. We see a kind of glow from the Big Bang, the sort of beginning of cosmic expansion. What you'd expect is that the universe would get bigger and bigger, but slowing down, that it would be decelerating, slowing down due to the presence of matter associated with galaxies, mostly dark matter. What about the technology? I said that, you know, people are not smarter than they used to be, but the phones are smarter. And then we have smartphones. And in the same way, the technology for making the measurements of distant objects has improved a lot. This is my thesis advisor, Bev Oak, and here he is holding, in about 1990, the world's largest digital detector, which cost more than if this thing had been made of platinum. I know that because he sold the platinum to get it. Anyway, it was 0.24 megapixels. Very impressive. What have we got today? Okay, you see, someone's also happy. This is John Tonry. This is silicon array of diodes. It's a charge-coupled device that can be used. It's all sensitive to light, and you can read it out. It's a billion-pixel camera that is on a telescope in Hawaii that I'll mention at the end. So the thing that changed, two things changed. The detectors became electronic detectors. We have computers to use them too, and they got bigger. So the idea is to find these supernovae. So here's Brian Schmidt, who's explaining to me, as I used to be, how he's going to do this. Here's the idea. I said that the supernovae are rare. There's one in a century in a galaxy. But think about it. That's 1 in 100 years. Whoa! That's 1 in 100 years. A year has about 50 weeks. Okay, take a couple of weeks off. Unless you're in France, then you have to take a month off. But anyway, that's about 5,000 weeks. So if you look at 5,000 galaxies, your chances of seeing one where there's a supernova that went off in the last week are pretty good. So it turns out that technology for looking at these galaxies and telling whether they have a new star in them or not has gotten better. Here's how you do it. Here's a picture you took last night, let's say, and here's a picture you took a month ago. The supernovae take about a month to get bright. And what you can do in a computer is to subtract one picture from the other, and the things that stayed the same will go away. The things that changed will show up. That's not so complicated. And in this pair of pictures, it's kind of interesting. You can't really see it very easily with your eye, but if you subtract this picture, last month's picture, from last night's picture, it turns out there's a dot there. Not only that, there's a red circle around it that shows that it really must be right. Okay, so this is the idea that with these modern detectors and computers, you can sift through thousands and thousands of galaxies. You can find a supernova any night you want. Now, it turns out there were two groups in the field. Here's Brian Schmidt. This is Saul Perlmutter. And here we're having a kind of discussion about whose group is doing a better job measuring the distant supernovae. It turns out that Saul got in the first jab. Whoops. Oh, well, we'll get to that. Never mind that. Never mind Adam. Yeah, Saul got in the first jab. I'll go back to that other guy in a minute. And they wrote this paper in 1997 that says, the results are inconsistent with lambda-dominated, that is, things that have a cosmological constant, low-density flat cosmologies. So the first result showed that the universe was slowing down. Well, it's turned out to be wrong. But the data got better very quickly. Adam Riess, here, now we'll go back to Adam. Sorry, I jumbled this up. I had another graduate student, Adam Riess, who was working on the question of how to do this problem of measuring distances to supernovae even when there's dust in galaxies, because there is dust in galaxies. And here's a picture of Adam in 1966. This is me in 1966. This is Bill Press. We were the co-advisors for Adam. In Massachusetts, it's okay to have two dads, so that's all right. And here's his notebook. Adam went to Massachusetts Institute of Technology, where they teach you to keep a lab notebook. And here it is. Whoops, here's his lab notebook. And he's got some data here, and he's trying to work out what is the value of lambda, this omega lambda. And if you put in omega lambda of 0, which he did, you get a mass for the universe that is negative. Uh-oh, this does not seem right. So he called me up. He said, I'm getting negative mass. I said, well, you've forgotten something, square root of pi, or I don't know what. Do this right. But it turned out it really was right. And that both teams, by the end of 1998, were showing data. Here's a Hubble diagram again, distance and velocity, where the span now is very big compared to the one that Hubble's Hubble diagram would fit down here. This is going out over a distance of a few billion light years. And what we see is that this line's not straight. It's curved, and it's curved in the way that you would get if the universe were not slowing down. That's this line, well, this line down here. You can see does not go through the distant points. It goes down here, it's kind of low. This horizontal line is for a universe that had the amount of mass we were kind of confident did exist. And the real points are up above that. Even without the complete analysis, you can see that. So anyway, by 1998, both teams agreed that we live in a universe that seems to have acceleration, speeding up. Here's today's sample of supernovae, much better sample, going from really nearby and low redshift to very far away and high redshift. And what you can't see is that that line is subtly curved in the way that's produced by a universe that's accelerating. What does that do? The light is coming to us from distant supernovae. If it travels in a universe that's going at a constant rate, it'll be a certain distance away. If the universe is slowing down, then while the light is in flight, the universe will not expand as much, the distance won't be as big, the supernova will look a little brighter. If, on the other hand, the universe is accelerating, the distance will be a little bigger, and the supernova will be a little fainter. And that's what we see. We see these things getting a little fainter. This line is slightly curved upward. And here's a calculation of that. The real data are shown, modern data are shown here, binned up at different redshifts and different distances. And what's ticking through here is different amounts of the dark energy, the stuff that is making the universe accelerate. And what you can see is, as it goes through here, the high values are the ones that fit the data well. If you have a value that's near 0, the line is down below the points. If you go all the way up to 1, it's a little bit above the points. But somewhere in between, and we think the best value is about 0.7, the line passes through the data. That means that the universe looks like it has 70% of its energy in the form of dark energy, the stuff that might be the cosmological constant, the stuff that's making the universe accelerate. This is a big deal. And so here is Saul Perlmutter. There's Saul. Here's Brian Schmidt. And here's Adam Riess in Stockholm in December, receiving the Nobel Prize for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So this is a big deal. Let me show you. This is the old data back in 1998, and this graph shows you what fraction of the universe is in the dark energy and what fraction in the dark matter. And you can see these kind of zeppelins of contours show you what the supernovae tell you. They tell you the solution is somewhere in here, which is not completely excluding 0, but it favors a solution that's away from 0. That 0 would mean no cosmological constant, the sort of thing that Einstein was thinking back about in 1930. 1 would mean the universe is completely full of dark energy. 1 on this axis is the dark matter, the gravitational part, which would be 1 if the universe were completely made of dark matter. And here's today's version of that diagram. So what has happened is that we've measured a lot more supernovae, we've done a better job, and now these contours are getting smaller and smaller, when we put them together with other data, you get this little tiny ellipse in here. Okay. So that's the evidence that we live in a universe in which there is acceleration. And I can tell you, Einstein is really surprised. Not only that, for those of you in the front can see, he's now carrying a sheaf of paper that begins with lambda on it, as if, I thought of this in 1916. Yes, very good. So here's the High Z team at the Nobel Prize ceremony. I'm ridiculously proud of this. There's me. There's one of my graduate students. He's actually photoshopped in. He didn't make it to the thing. Yeah, here's who's that? Adam Riess. He's one of my students. There we go. Adam Riess, one of my students. There's Brian Schmidt, one of my students. They're holding the trophy here. There's Bruno Leibengut. He was my postdoc. There's Saurabh Jha. He's one of my students. There's Peter Garnovich, one of my postdocs. There's Pete Chalice. Anyway, a lot of my pals were involved in this. In the old days, they used to give the award to the thesis advisor, but I guess they've just changed their tune. This is for real. I have received the Extravagant Universe license plate from the state of Maine. And in a curious demonstration of the Doppler effect, I was passed by the guy from New Hampshire that has XLR8N. I don't think he's a cosmologist. It was a Jaguar, and he was going very fast. Okay. So here's the diagram of the contents of the universe. The dark matter, whoa, go back. Stop. The dark matter is about 23%. The atoms that make up you and me, the stars, the galaxies, everything is about 4%. I don't know how that makes you feel. Makes me feel special. And the dark energy, the stuff that's making the universe accelerate, is about 73% of this diagram. Now, here is why you should be pleased by this diagram. The diagram is full, but you should ask, what is it full of? And it is full of our most important resource in science, which is ignorance. We don't know what the dark matter is, and we don't know what the dark energy is. These are things which maybe you will have a chance to find out. So this is good. You know, ignorance is good. Okay. But it is a little puzzling. I went to an institution in another country, and they had a gift shop. And the gift shop had T-shirts with funny sayings on them. And I was looking at them. There were the funny things that Einstein had said and so on. And there was this funny thing that I said that was on the back of one of these. It said, the universe is under no obligation to make sense, but your thesis should, you know. And I said, but Robert, that's me. And they said, we'll give you a good discount. Which they did. So what is the dark energy? Well, in the old days, you used to just Google it, you know? And instead of getting some propaganda from the Lawrence Berkeley Laboratories or from Harvard University, you got this in the old days. You got from American Hydroponics this thing about plant food. This is to grow controlled substances in your closet. And it was called dark energy. And we don't know much about the dark energy, but we know it smells bad. These specialized processes, it says, are also responsible for the very distinct odor of dark energy. Okay, but what about physics theory? Well, I am an observational astronomer, but it turns out I have a union card from the International Brotherhood of Theorists. They turn coffee into theorems and cigarette, I don't know. Anyway, you'll be interested to see this is valid to infinity. Signed by David Gross. He did win the Nobel Prize. So this is the real thing, as good as Photoshop can make, of my authority to talk to you about the physics of the dark energy. So let me do that. Is it the cosmological constant? I think that's the question. It could be something else. It could be that there's some other thing, not the cosmological constant, which would be a property of empty space itself, the vacuum. That there could be some other thing, another field that's present that perhaps is not constant. People have thought about that. There could be modifications to gravity. That is, Einstein's theory of gravity has withstood every observational test, but it may not be perfect, and it may not work perfectly over cosmological lengths. Couldn't there be some change? Well, you can't tell just from the expansion history, what I've been talking about today. You also have to measure how things have clustered over time, and people are working on that. If you ask a theoretical physicist, though, please, would you estimate for me the energy associated with the vacuum due to gravity? They'll say, why, of course. They'll take out their fountain pen, shoot back their cuffs, And on the back of an envelope, shown here, calculate the value of the energy that's associated with the length that corresponds to gravity. And it turns out in units where the observed value is 0.7, the theoretical value is 10 to the 120th, a 1 followed by 120 zeros. This is what in academic circles we call not good quantitative agreement. And it shows that there's something very important missing, which is our understanding of quantum gravity. There must be some way to understand why the value, well, there might be some way to understand why the value of the cosmological constant, if that's what it is that's making the universe speed up, is so different from the one you would calculate naively. So there's something we don't understand about how gravity works when you get to very small scales. Okay, so how do you think about this? When you see those pictures of the galaxies, you have to realize most of what you're seeing is not the galaxy. Most of what you're seeing is due to the dark matter that's present, that's keeping the stars in their orbit. This is not so mysterious. Okay? When you look at this picture, you say, oh, look at the snow. But it's not the snow, grasshopper. It's the mountain. In the same way, the thing that you see, you know, a mountain by moonlight, where you see the snow reflected, is not the mountain. Most of the stuff is invisible. And in the same way, that's true here. Keep that thought in your mind as you travel across this bridge. Similarly, the dark energy is kind of an invisible thing that's making the universe expand. But you're used to that. Look at this. Here's a painting, and it shows some trees, and the trees are in motion. What's moving the trees, you might say? And everybody says, well, it's the wind. You don't see the wind. You see the motion of the trees. That's the effect of the wind. Keep that in mind, grasshopper, as you go on your voyage. Okay, so we're used to ideas like this, where we see the effects of things, and we infer their presence. The things are kind of mysterious, that's for sure. But the idea that we would use the motions in the universe to figure out what the forces are, the tug of war between gravity and this kind of anti-gravity stuff, this cosmological constant or whatever it is, the dark energy that's making things speed up, that is not such a crazy idea. Okay, if you want to know more about this, I couldn't recommend a better book than this one, which is still in print from the Princeton University Press. And let me say just a couple of words about the future. Where are the anti-gravity boots? That's what I want to know. Haven't gotten those yet. I showed you this picture of a guy with a big CCD camera. That is actually mounted on a telescope in Hawaii, and we're using it to search for supernovae. We find dozens every night, and some of them are of great interest for measuring better what the properties of the dark energy are. We want to know, is it the same as the cosmological constant, or could it be different? And this is one way to find out. So we're finding the supernovae, and then we're measuring them with the Hubble Space Telescope. I got the time to do this, I'm so proud to say, after being rejected twice. Anyway, I got the time to do this. We're going to start this month, in the month of October, with this program to measure the distances using the Space Telescope. One more thought about the distant future. I said that the Andromeda Galaxy is about 2 million light years away, and you may remember, if you're very sharp, that I said that its velocity is actually toward us. And so you can work out when it will get here. We see galaxies collide, and in fact, there will be a collision someday between the Milky Way and the Andromeda Galaxy, depicted here. And in fact, people are worried about it. I don't know if you saw this in the New York Times. It's from last May. Maureen Dowd is not only, she's upset by this, as she is about many things. Anyway, she's upset about this Andromeda coming. So this is what things might look like in the year 4 billion, 1917. And then two things will happen that will be kind of interesting. One is, if the dark energy is really at work, the expansion of the universe is literally exponential. That means the bigger the universe is, the faster it expands. We won't be able to see the more distant galaxies because they'll be moving away from us faster than the speed of light. Their light will get redshifted away completely. It'll be a cold, dark, empty place. Andromeda will collide with us, and there will be just one big galaxy in our universe, just the way Einstein thought it was in 1917. So what this tells you is we only have 4 billion years to do this work. So when I describe our ignorance as an opportunity, it doesn't mean you can be lazy. You have to get right to work on it. Okay, so that's my story. The visible universe is the effect of invisible forces at work, that the expansion of the universe is a kind of competition between gravitation and this dark energy, and that there's been a change between a universe that was expanding but slowing down, decelerating, to the present day where the universe is accelerating. It's as if you threw a ball up and instead of coming back down, it just took off. Okay, so one last word about science. What is science for? Well, if you talk to people, they often say, well, you know, science is very important because it leads to technology, and that really makes the economy go, and that's true. If you talk to people wearing kind of funny hats, they often say, well, you know, it's very important for defense because we want to be ahead of it's a dangerous world, and we want to be ahead of other people in knowing things. A lot of congressmen are kind of old guys, and they're very interested in preserving life, and, you know, I'm against disease too. So often they talk about the effect of science on prolonging life. These are all good things. I'm in favor of these. I'm in favor of being rich and safe and immortal. But that's not all there is to life. People want to know where we came from, where we are in the universe, in space and in time, and where we're going. So I don't think it would be ideal if we were rich, safe, immortal, and bored. I think we ought to do at least some science for the joy of finding out how the world works. Thank you very much.
Thank you very much for that. I think we have time for a few questions. Yeah.
Two quick ones. One, the cosmological constant that Einstein said, we now think it's the same constant that makes it expand?
Could be. It turns out that Einstein had not really thought this through very carefully. That the static universe that he was talking about is one that was an unstable equilibrium. It's like standing a pin on its head, that you could make the forces balance, the gravitation and the repulsion that corresponded to the cosmological constant. But if you push the universe at all, it would either expand or contract. Einstein, however, he thought that was so crazy, he didn't even do the solutions that change with time. And that was done by other people. It turns out a Russian, Friedman, did that computation and sent it into the journal and Einstein wrote back and said, this must be wrong. It was Einstein who was wrong. Another blunder. And later, Lemaitre, a Belgian priest and PhD from MIT, unusual combination, did dynamic solutions like that. So yes, it could be the same cosmological constant, but not quite in the same way that Einstein meant it. The modern view would be a quantum view, that you look on smaller and smaller scales, the uncertainty in the energy is big. That's where you get that 10 to the 120 figure. That's not quite right, but it would be something along those lines. Yeah, these high school students. Is it the light travel time? What? Yeah, go ahead.
I have two questions. One is it possible that the universe is expanding in a non-uniform way, which would account for this?
Yeah, a very interesting question. So, for example, you can imagine that the universe is lumpy and that there was a lump of dense stuff outside our view and that somehow the stuff in our neighborhood is being pulled toward it over time. That's an idea. People have worked out the consequences, and it seems that that is contradicted by our measurement of the glow from the Big Bang, the cosmic microwave background, which I didn't have time to talk about. So that's one of the ideas that came up fairly quickly, and it is an interesting one. Another thing that we should do, I showed you that graph, and I said, now we've measured 500 supernovae, and we have measured this to a gnat's eyelash, and so on. But that's only averaging over the whole sky. And so a smart thing to do, which I have a graduate student that I would like to have work on this, so if any of you would hurry up. But if you could measure 500 in each of, say, 10 patches around the sky, then you could find out whether this acceleration was, in fact, the same in all directions. That would be a really interesting thing to do.
The other question is a very quick technical one. If you can detect the type 1a supernovae from the ground, why do you need the Hubble Space Telescope to measure their redshift?
Well, we're measuring the brightness in the infrared. It turns out the Earth's atmosphere is quite opaque in the infrared, or emits in the infrared, and that's what we're doing with the Space Telescope.
It's not their redshift, but it's basically their...
It's the transmission of the atmosphere. It's blocked out. Yeah, you're welcome. Yes, excellent. You must be from the back of the room. No, go ahead.
There is a notion that the universe would be that basically space is a sort of loop that it will in one direction.
Yes. Yes.
Like how is that a serious notion?
Right. So the question is, couldn't there be curvature to the universe so that you travel out in some direction, you come back and shine a light on the back of your head? Turns out Einstein's original static solution was something like that. It was a space that was curved, and although there was no boundary, you would come back to the same place. So the geometry of the universe, four-dimensional space-time, is a little hard for us to imagine because, that doesn't usually happen to us. But if you think about it, imagine the surface of a sphere, the Earth. If you say, okay, you travel as far as you want to go on that curved surface, a two-dimensional surface, we are super beings out here in 3 dimensions watching you do it. But you could go around and come back to the same place. So that sounds paradoxical. It sounds like you can't get your brain around it. But in fact, it could be true.
No.
I didn't say you couldn't get your brain around it.
I understand. I was asking,
Is it?
Could it be?
Yeah, the curvature is not big enough. No, the geometry of the universe, this is kind of we're in a place, the Geometry Institute. The geometry of the institute, of the universe, is Euclidean geometry, surprisingly enough. It's flat space. Even though Einstein's relativity provides this possibility of curved space, the universe that we actually live in is only one of many. That's why mathematicians have a broader view of things. But anyway, it's only one of many possible universes. But the one we live in seems to be very, very close to flat, which means that the Pythagorean theorem holds, and the circumference of a sphere, and the volume of all those things that you learned and that are up on the wall as you walked in are true in Euclidean space, in 3-dimensional flat space. We didn't have to live in a universe like that. It could be, Einstein showed how the presence of matter in the universe curves space and could make it a different one. But it turns out that the universe that we actually live in has this property. It's very nearly, that diagram was full, that pi diagram I showed you. It's full, it's 100%, that's exactly what you need to get flat space. So it's a curious thing. Okay, I'm going to let another person ask why you cogitate there. Okay, yes, I see you're wearing red, shifted.
Can it be so big that the universe appears flat?
Yes, that's what people say. So the idea is you have a universe which might have had any kind of curvature you like, but which has expanded from more or less the size of a grapefruit to the size of the universe we see today, and that any curvature that it had at that early time has been kind of inflated away. That is, the universe has gotten so much bigger. It's like a balloon. If you expand it enough, it looks flat. By the way, did you know the Earth was spherical? But you'll go outside and it looks flat. And that's because the radius is big. You just see a small patch of it. You're kind of small compared to the size of the Earth. And in the same way, something like the same way, the idea is that if the universe had any curvature you like, but expanded a lot, that would essentially go away. And the current notion, which I didn't talk about, is that there was this inflationary epoch early on where something like that happened. Yeah?
If by some chance we went back in time and we took the...
Now you're talking.
And we just pushed it ahead 4 billion years and we formed in the in the universe where we can only observe our own galaxy, would there be any way to figure out all of what you just talked about, or are we completely dependent on light?
Wow, wait a minute. Time travel and no light. All right, first let me say this. We think that the Earth formed about 5 billion years ago. I was talking about measuring the distances to supernovae that are 7 to 10 billion years in the past. That's on those plots. So wait a minute. So I'm just saying that this acceleration started about the time that the sun formed and the Earth formed and so on. The chemical elements that are in the Earth and in the sun are from generations of stars that took place before then and were in the Milky Way galaxy and then somehow formed into stars and planets. Now we have the time travel. So if you went back to that era, the universe would not be accelerating. It would have been decelerating, and there was a change from deceleration, because the density of matter was higher, to acceleration. And that inflection point, that change, took place about when the Earth was formed. So I think I'm answering your question now, I think. If we were astronomers 5 billion years ago, we would have measured a universe that was not accelerating. And as I said toward the end, if we go 10 billion years into the future, there's not going to be any galaxies for us to measure. So I think in this limited sense, we live in a very special time. 15 billion years of special time. And whether that means anything or not, I don't know. I don't know. But it shows your thinking. And the other thing is, it gives me the opportunity to make the classic dynamical joke, which is everybody knows that the change in position is called velocity. And everybody knows that the change in velocity is called acceleration. And everybody knows that the change in it, not everybody knows, but most people know, that the change in acceleration is called the jerk. And this would be the cosmic jerk, the change from deceleration to acceleration. And there was a picture in the New York Times of Adam Riess, my graduate student, under a headline that said, "The Cosmic Jerk," and then it just went on to describe it. Even his mother didn't like that. Yeah?
You talked about how space is expanding between galaxies.
Yes.
Within our galaxy.
Yes, very good question. So the question is, I talked about the distance between galaxies getting bigger and space stretching out in that way, but what about inside galaxies, or, in the solar system, or in the Earth, or, your hand? So what we say is that on small scales, there are forces holding things together. So electromagnetic forces for ordinary material objects like this building, gravitational forces for big things like planets, and that the effect of the local gravity is much, much more important than the cosmological stretching out, so that those things, we think, are not expanding, and that they're separated out from the overall expansion. But you notice I was waving my hands a lot. This is always a sign that the explanation seems a little, appealing to emotion. But you really can show that the separate pieces of the universe don't share the cosmic expansion. Yeah?
In the pie chart before, you showed atoms being distinct from dark matter.
Yeah.
So does dark matter have any sort of particles associated with it?
Very good question. So the question is, what is the dark matter? Is it a particle or what? I don't know if any of you saw the Ig Nobel Prize ceremony last week. Did anybody see that? Well, anyway, these are sort of comic things that are awarded. And I gave the keynote address in which I showed that pie diagram, and then I sliced out the 4% that's baryons, and I ate it because it was a real pie. That was sort of funny to me. And I said that baryons were the tastiest part of the universe. But you're asking what's that other 25%? The best answer people can give is that it has to be something that does not participate in nuclear reactions that build the elements in the early moments of the Big Bang, because we know about those. We know that there would be helium, the second element, would be synthesized as the universe cooled. The particles, the neutrons and protons would bump into each other and make an amount of helium, and that's the amount we see. So it can't be that the density of that is really 5 times higher. In other words, the dark matter can't be neutrons or protons. It cannot be ordinary matter of the stuff like the kind we're made of. Luckily, we know of other kinds of matter. So for example, neutrinos are weakly interacting particles. They don't participate in those nuclear reactions. They're real, but their mass is too small. They can't be the dark matter particle because the mass is too small. So what you need is a particle that has weak interactions, like the neutrino does, but a big mass. So you go to your particle physics friends. You say, particle physics friends, you got any particles like that? They say, oh yeah, we got dozens of them. And the lightest supersymmetric particle might actually be stable. So people take this very seriously. There may be such a thing, and people are looking for the interaction between laboratory experiments and this haze of particles. Because it must, if it's dominating the universe, presumably it's in our Milky Way galaxy. The Earth is going around the galaxy at 200 kilometers a second. So it's like driving through a mist. We're going 200 kilometers a second. There's a mist of particles, which would be these dark matter particles, orbiting the center of the galaxy. And if you build a detector that has many kilograms of stuff, you should expect one interaction every month. Bing! Of course, there's a lot of other stuff going on, cosmic rays, radioactive decay, all this background. But there are experiments that are being conducted right now to look for the weakly interacting massive particle, WIMP, WIMP, which would be, that's our nickname for the one of the candidates for the dark matter particle.
After thousands of years, we've reproved Aristotle's ether.
No, I wouldn't say that. I wouldn't say that. But we might be in a medium that's made of particles, that's gravitationally bound to the galaxy, that's for sure. So it's not, I have Plato, that's in the talk this afternoon, I think. I have, this same ideal means Plato. So you can come back and I'll try that out.
Let's take one last question.
All the way in the back. I'll hear your, why is everyone laughing? You know this person.
Why do we always call dark energy when it kind of acts like a force?
I'll tell you why. First of all, we made up the name. Okay? I mean, not me, but Mike Turner. And he wanted to make up a name to indicate that it could be something besides the cosmological constant. I mentioned that briefly. There could be something that changes with time. Quintessence is kind of a catchphrase for those models. And if you look in the astronomical literature, the astrophysical literature, there are hundreds of speculations about what this stuff might be. So he wanted to have a term that was bigger than the cosmological constant and included these other possibilities. So he thought dark energy was a good thing because it kind of sounds like the opposite of dark matter, which it sort of is. There's a tug of war, dark matter trying to slow things down, the dark energy trying to speed things up. And it meant you could go to the United States Department of Energy and ask for money to do the research.
With that, let's thank Dr. Kirshner again.
Thank you. Thank you. Okay, my pleasure.